In the previous video, we have seen that when monochromatic light goes through two slits, it will produce an interference pattern which will have bright and dark fringes. The path difference is equal to d sine theta, where d is the spacing between the slits, and theta is the angle of the rays with the normal of the slits. And we have seen that when the path difference is equal to m lambda, where m is any integer number, then there is constructive interference. And when the path difference is equal to m plus 1/2 lambda, again with m any integer number, then there is destructive interference. We also reviewed the equation for the intensity, and we saw that it is equal to I max times the cosine square of delta phi over 2, where delta phi is the phase difference between the two rays. And so in this video, we will review the question, what will happen if we increase the number of slits, right? So instead of 2 slits, we have 3 or 4 or even 10 slits. So are the bright areas moving further apart? Or are they moving closer together? Or is the spacing the same, but the bright fringe are narrower? Or is the spacing the same, but the bright fringes are becoming broader? So I'm going to redo the demonstration with a laser and the plate that contains various kinds of slits. In the previous video, the demo was not very good, so I will start with 2 slits again. So this time you will be able to see it. I will move the camera closer to the board. So you will see the interference with 2 slits, and then I will increase the number of slits. So pay attention to what happens to the interference pattern. Two slits, then 4, there you go, and then 6, and then 8 or 10. This is actually 10. All right, so you see that the spacing between the bright areas remains the same, but they become narrower and also more intense. So to explain this, I'm going to reuse the concept of phasor. So we introduced this at the end of the previous video. So if you don't remember, you can pause this video and check the last minute of the previous video just quickly. So first, let's start with constructive interference. The path difference between 2 successive rays is still the same, it's d sine theta. So either we can write the path difference has to be m lambda, or we can write that the phase difference has to be m times 2 pi. Right? Both descriptions are the same. But we're going to work with the phase difference in this lecture. It's a little more convenient. In terms of phasors, if we have 2 slits, then we have 2 phasors, and the angle between them is m2 pi, so the phasors are essentially aligned. And if we have 8 slits, we have 8 phasors, but the angle between 2 of them is also 0 or 2 pi and so on, and so they are all aligned to each other. So you see that if we have n slits, then the amplitude will be proportional to n. And since the intensity is proportional to the square of the amplitude, then the intensity will be proportional to n squared. So 2 important results already. First, the position of the bright fringe is the same as when there was only 2 slits. And second, the intensity increases with the square of the number of slits. And this is normal because you have more slits, so more light is going through the plate, and so there is more intensity. Now, let's look at destructive interference. Again, you can write that the path difference has to be equal to m plus 1/2 lambda, where m is any integer number, or in terms of phase difference, this is the same as writing that the phase difference has to be equal to m plus 1/2 times 2 pi. So the phase difference is plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on. With phasors, if you have two slits, the second one will be rotated by plus or minus pi compared to the first one. In this graph here, I shift the phasors a little bit down so that you can see them, but really they're on top of each other, and we come back to the same position as where we started, and so the amplitude will be 0. If you have 8 slits, then the third one will be rotated by plus or minus pi compared with the second one, and the first one will be also rotated by plus or minus pi compared with the third one, and so on and so forth. And so again, in reality, they are not shifted. The endpoint is the same as the start point. And so in the end, if you have an even number of slits, then we're also going to get 0 amplitude. But there is another way to get 0 amplitude with 8 slits. Right? Let's imagine that the phase difference is equal to pi over 4. Then the second phasor is rotated by an angle of pi over 4 compared with the first one. And the third one is rotated again by pi over 4 from the second one, and so on. And you see that we arrive to 0 amplitude again. Let's look at another example. If the phase difference is pi over 2, then the second one is rotated by 90 degrees, and the third one is also rotated by 90 degrees compared to the second one, the first one, and so on. And so again, in the end, we arrive to 0 amplitude. So what you see is that with many slits, there is more ways to get 0 amplitude. There is always one way to get maximum amplitude, right? To get maximum amplitude, you will get this when all the phasors are aligned and the phase difference is a multiple of 2 pi. But there are more than one way to get 0 amplitude, right? With 8 slits, it can be that the phase difference is pi, or pi over 2, or pi over 4. And so in fact, for n slits, you can see that the smallest phase difference that will give you 0 amplitude is equal to 2 pi over n. Right? In that case, adding n slits will make you one full rotation, and so the amplitude will be 0. So we will get 0 each time n times delta phi is equal to m2 pi. That means each time we do a full turn, or 2 full turns, or 3 full turns, and so on. And this can be written as delta phi is equal to m2 pi over n, with m equal to 1, 2, 3, and so on. But not when m is equal to n. Right? In that case, delta phi is equal to 2 pi, and this is the condition for constructive interference. Right? This is when all the phasors are aligned. And so in summary, we will get n minus 1 minima between each pair of principal maxima. So with 2 slits, we have 1 minima. With 8 slits, we have 7 minima. And with 16 slits, we have 15 minima, and so on. So you see that the peaks become sharper and sharper as we increase the number of slits. And because the peaks are really sharp, then we can easily and precisely measure their position. And because the position is given by d sine theta equal m lambda, you see that it depends on lambda. And so different colors will have different theta and different positions on the screen. So when you have a white light source that goes through a diffraction grating, which diffraction grating is a plate with a very large number of slits, then you will see all the wavelengths that were part of the white light, and we will see each color several times, in fact, because of the different values of m. So on this schematic, for example, you have the bright spot at the center, which corresponds to m equals 0. So for m equals 0, all the angles for the different lambdas are 0, so you just get white light in the center. But then you have a series of colors on both sides corresponding to m equal plus or minus 1, and then another series for m equal plus or minus 2, and so on. The diffraction gratings, they can be used to measure the spectrum of light from a source, and this technique is called spectroscopy or spectrometry, and it is a very, very important application in science. Different atoms or ions absorb or emit light of different wavelengths, and so a diffraction grating can be used to identify the elements, the atoms that emit the light. So for example, hydrogen will emit only a few specific wavelengths, and helium will emit at some different wavelengths. And so with a diffraction grating, we can distinguish these two elements. And using a diffraction grating is very simple. Actually, let's see if we can do it with the camera. So I turned on a helium lamp, and then I will bring a diffraction grating in front of the camera. And so if you look on the side at higher angles, you can see the colors corresponding to the different wavelengths from the atoms that are in the lamp, right? And so that is what is called spectroscopy. And what is really nice is that you don't even need to touch the source. The source can be very far away, and you can learn something just from the light, right? So you can use this to deduce the chemical compositions of stars, for example. That's actually how we know the chemical compositions of stars. Last example, have you ever noticed that you can see rainbow colors on a DVD, right? What is this? Well, it's physics 9b again. Right? In fact, on a DVD, you have tiny pits that are separated by a distance that is of the same order as visible light. And so the DVD is acting like a reflection grating. Right? It's a grating, but in reflection. And it will produce this kind of rainbow colors when natural light is reflected on it. Now, there are a lot more to say about diffraction gratings, right? Because of COVID-19, I've decided to reduce the content. One thing that we will not cover this year is the chromatic resolving power, but essentially, the larger the number of slits, the better you can separate different wavelengths. And so in this example of the grating demo, you have in fact thousands of slits. And we also don't have time to cover X-ray diffraction. In fact, because of the periodic arrangements of atoms in a crystal, you can consider a crystal as a kind of diffraction grating, but for the wavelengths that are in the range of 10 to the minus 10 meters. So that kind of wavelengths are called X-rays. And so using X-ray diffraction, we can learn from the atomic structure of materials. Right? This is actually a very important technique in my own research in my lab. And so if you want to learn more about this, don't hesitate to ask me during the office hours.